and you came in. If you didn't grab one, there are pictures. Tonight's picture is of the Crab Nebula, and that parentheses says M1, which means it's the first object in Charles Messier's catalog of things that aren't comets, because he didn't care about all these wonderful nebulae and galaxies that he found. He actually cared about looking for comets. This is the very first object in Messier's catalog. If you want to know more about it, well, I'll tell you a little bit more in the news summary, and you can read on the back about it, okay? But if you didn't grab one on the way in, please grab one on the way out. Tonight's talk will be Amber Straughn from NASA Goddard, telling us about dark energy in new worlds, NASA's WFIRST mission. This is a sneak preview of astronomy that will be coming in the next decade or so. All right, coming up on July, our July talk was normally be on July 4th. We are not going to do that. Instead, we're doing it on the week after, and our speaker, to fit his schedule, we're putting it on a Monday, not a Tuesday. Monday night, same time, 8 o'clock, same place, right here. How to find an inhabited exoplanet. If that's not an intriguing title, I don't know what could be, okay? David Charbonneau from the Harvard University. In August, we go back to our standard First Tuesday with a really cool talk. I'm very much looking forward to this. Courtney McManus is talking on the view from mission operations. One of the cool things you get by coming to the Space Telescope Science Institute is, yes, we give you all this wonderful science, but we also can give you the background, the details, what's happening behind the scenes. So this is definitely a behind-the-scenes talk, and I haven't heard Courtney speak before, but everybody tells me she's really wonderful, and she has a great perspective. Yes, Karen's giving me the thumbs up there. So please come in August. In September, Nolan Walborn, who has spoken every other year for me. He's a wonderful, reliable speaker for the Public Lecture Series. He's talking about active luminous blue variables. That's an intriguing title. I'll tell you more about that next month. You want to find out our list, you go to our website, go into your favorite search engine, put Space Telescope Public Lecture in, and you'll find this web page where we have the list of the upcoming lectures. We have the links to watch it live on the Space Telescope webcasting, as well as on our Hubble site YouTube. You can watch the past lectures. We have recorded these lectures since 2005. That's 12 years of astronomical goodness you have to review. It'll take, if you want to binge watch, it may take you more than a weekend, okay? We have several seasons out there. Oops. And you can also sign up for our email announcements. I checked I had to do a report. We have over 550 people on our email list. So lots of you have signed up for our email announcements, okay? All right, speaking of the announcements, sign up at the website. You can do this, but it's much easier just to do it at the website. If you would like to contact us and send us email, ask us questions, you got a suggestion for an amazing speaker or something, send email to publiclecture@stsci.edu. You can also follow us on social media. We have Facebook, we have 2 Twitter accounts, we have Google+, we have Pinterest, and maybe a few other things that I'm not quite aware of, but I have to update this because I know we're starting a new push in social media next month. So by August, I'll have a slightly revised version of this slide. Not this part, because this is all I do. I do my blog, I do a little bit of Facebook, a little bit of Google+, and a little bit of Twitter. So don't expect me to be tweeting 20 times a day. The observatory, I think the weather is permitting. I didn't get an email, but if weather is permitting, Irini will be here at 9 o'clock and watch the last part of Amber's talk and take you across the street to look through this, which is the Maryland Space Grant Observatory, okay? So make sure I don't forget about this. At the end, somebody wave at me and say, Frank, don't forget the observatory, because it's easy once we're on a roll with all the cool questions people ask. All right? And now, news from the universe for June 2017. Our first story tonight, the final frontier, fields. So Hubble has started as it's going, these projects called treasury programs. These are very large projects that would never get funded for this amount of Hubble time unless there was a special program saying, hey, yes, you can have hundreds of orbits of Hubble time. And one of the ones we've been talking about the past couple years is called the Frontier Fields. It's a very ambitious program to look at 6 galaxy clusters, okay? And these are see these red squares here? Those are the 6 galaxy clusters. And these are some of the most massive galaxy clusters in the universe. So massive that they produce the effect of gravitational lensing, okay? And so we look into these galaxy clusters to see examples of gravitational lensing, which I'll show you in just a second. But they can also observe at the exact same time these blue fields, which will be some parallel fields to them, and we call them the parallels, but they are also deep fields, like the Hubble Deep Field, the Hubble Extreme Deep Field, etc. They are very deep looks at the universe. And when we look at these small deep fields, we get a very small patch of the sky. One Hubble pointing is about 1/12,000,000th of the entire night sky. And so you need a lot of these deep fields to add up the statistics to understand the deep universe. So the Frontier Fields was this ambitious project to really study these galaxy clusters as well as study the deep fields. And they've released, over the years, they've released 5 of these galaxy clusters, and just a few months ago we released number 6. This is the galaxy cluster called Abell 370, okay? And all of these white objects in here are the galaxies of the cluster. And their combined mass warps the space and produces gravitational lensing. And so the image of a galaxy that passes through this cluster gets warped and stretched by the galaxy cluster. And one of the famous examples in Abell 370 is something we call the dragon, okay? This is not 1, not 2, but 3 images of the same galaxy. All right, and you can sort of see it here on the tail, on the head of the dragon. You can see that looks sort of like a normal galaxy, right? But here's another image of it in the middle, in the midsection, that's become stretched out due to the gravitational lensing. And then there's another one on the other end, the tail of the dragon, where you can see it's also an image of the galaxy cluster. So the light from this galaxy has traveled 3 paths through the cluster and produced these 3 distorted images of this galaxy. And we call it the dragon just because it has a nice head and tail type features to it. And you can see a lot of other streaky and arcy things through here that are other evidence of the gravitational lensing. All right, and so this is something that they're searching for very distant galaxies and really cool examples of gravitational lensing in this. We're also looking at these deep fields, and here is the deep field that parallels to it, and it looks very much like the other deep fields. And as I said, this will augment the statistics of our understanding of these deep fields. So this is sort of the announcement of that, hey, we've got all the data. We haven't by any stretch of the imagination done all the analysis, but we have all the data for all 6 galaxy clusters and all 6 deep fields. It's kind of nice that this project that's been going on for like 3 or 4 years has finally got all the data, and of course the science that will come from it will take many, many more years to continue to trickle out, because we're getting lots and lots of science out of not just the current observations, but also the archival observations from Hubble. Our second story, a dramatic chromatic Crab nebula. Now, there's a reason I use this image as our giveaway tonight, the Crab nebula, because this is the standard image of Hubble's view of the Crab nebula that everyone knows. It came from 2000 or 2001, done with the Wide Field Planetary Camera 2. And it's a really cool image. It's great. And so when people think of Hubble's Crab nebula, this is what they think of. But there's more there's more to the Crab nebula than meets the eye. So in this image, we see that the different colors represent different specific elements, like nitrogen or iron or sulfur or hydrogen, very specific elements, and they tell us what's going on for the temperatures and densities that are appropriate for the emission of those spectral lines. But what if we went beyond visible light? What if we looked at the Crab Nebula over many different wavelengths? We would get an even greater view of it. Okay? Actually, you know what? There's probably a bunch of you who don't know what the Crab Nebula is. How many people don't know what the Crab Nebula is? This is one of these problems with being an astronomer. It's like, oh, yeah, the Crab Nebula. The Crab Nebula, for those who don't know, and actually surprisingly few, is a supernova remnant, a star that exploded 1,000 years ago. Chinese astronomers saw the explosion in, actually, I believe it was July 4th, 1054. All right, so that was a little early for Independence Day, but in 1054, they saw a guest star appear in the sky. And it was a star that just basically exploded. All right, it blew its guts out into space. So 1,000 years ago, all that gas was inside a star, and now it's a nebula that's 10 light years across. Okay, so it's booming across space at millions of miles an hour. All right, so this is the guts of a star blown out into space. And if this is what we see in visible light, if we look in radio light with the very large array, we get this image. And so these are the radio waves emitted from the gas that is being energized to emit in radio. Now, radio waves are generally the lowest energy that we look at, okay? So this is out here. You can see it's mostly the outskirts of the nebula. If we then step up to infrared wavelengths, from the Spitzer Space Telescope, we see this. This is the cooler gas. This is gas around a few hundred degrees, all right? A few hundred degrees, and you start to see, you know, the filamentary structure. If we go to the Hubble image and we just give it a single filter color, all right, here we're getting gas that's at thousands of degrees generally, thousands or tens of thousands of degrees, and you really see that filamentary structure, the gas that's blown out and created all these beautiful filaments. All right, if we then go up to the ultraviolet, now we're looking at gas that's tens of thousands to hundreds of thousands of degrees. And you sort of see the volume filling inside the filamentary structure that we see in visible light, but you also start to see the appearance of a disk-like in the center of it. And when we go to X-rays, the highest energy, you really see that disk. And so you see the disk of material around this bright spot in the center. That bright spot in the center is a neutron star. It's the collapsed core of the star that exploded, and this one happens to be spinning 30 times a second. It's a millisecond pulsar. Right? And you can see this disk of material around it, as well as what appear to be material streaming out from the poles of it. Okay? All right, so combining all those views together, you get the multi-wavelength view of the Crab Nebula. And this includes radio, infrared, visible, ultraviolet, and X-ray views from telescopes. And I think it's a really gorgeous image, and I think it showcases where astronomy has gone in the last 100 years. Because 100 years ago, we were just using visible light. We didn't start using radio light until the 1930s. And we have developed observations across the entire electromagnetic spectrum. And here's a gorgeous example of it with the Crab Nebula. The third story is yet more from the lunatic fringe. Now, those of you who've been here many times have heard me discuss the lunatic fringe before. And what I refer to with that joke is first the fringe of the solar system. So here are the orbits of Jupiter, Saturn, Uranus, and Neptune, okay? And so out beyond the orbit of Neptune is what I'm referring to as the fringe of the solar system, and it's a region we call the Kuiper Belt, okay? And the Kuiper Belt is something that we didn't know about until the 1990s. We discovered these thousands of objects out beyond Neptune, well, except for 2 of them, all right? Except for 2 of them, we discovered thousands more objects out beyond the orbit of Neptune. They're small, they're icy, they have elliptical orbits, they have tilted orbits, all right? And they're very much just like their the largest object in the Kuiper Belt, which is Pluto. Pluto was discovered in 1930, Charon in 1978, I think, although it wasn't verified till 85. something like that. All right. And then, so Pluto and Charon are the first two objects discovered in the Kuiper Belt. We now know of thousands. All right. And when I talk about lunatic fringe, I'm talking about the moons around Kuiper Belt objects. And Pluto is a great example because, as I said, we knew about this before Hubble. It took Hubble's resolution to find Nix and Hydra, which we found in 2006. Kerberos, I think, in 2010, and Styx in 2012. So Hubble has been instrumental in finding these moons around these objects at the fringe of the solar system. All right, so here's a graphic of the 8 largest Kuiper Belt objects. All right, everyone knows Pluto. Can anybody name other Kuiper Belt objects? Astronomers without, yes? Eris, yes? Haumea, yes, very good. Other ones? In the back? Maki, excellent. All right, so these are, yes, interesting names, okay? Pluto, Eris, Haumea, Maki, those are the traditional top 4, Quaoar, Sedna, and Orcus, okay? Yes, it is pronounced Quaoar, okay? Now, you'll notice I have left out a name for the 3rd largest Kuiper Belt object because it has no name. It is actually known by its catalog number, 2007 OR10. It has yet to be given an actual name, which is kind of funky because there's a lot smaller things out there that have been given names. Now, when I talk about the moons of Pluto, there are lots of them, but there are also lots of moons of other Kuiper Belt objects. Eris has Dysnomia, there's Hyaka, Namaka, Waywatt, Vanth, and MK2 is a nickname. I don't know if it actually has a real name or it still has a designation. All right, so you'll actually notice of the 8 largest Kuiper Belt objects, only Sedna and 2007 OR10 don't have moons. Or, well, I say didn't have moons, okay? The Kepler mission looked at 2007 OR10 and found that it was rotating slowly. It rotated once every 45 hours. Generally, Kuiper Belt objects rotate in a couple hours. So having a 45-hour rotation suggested that some of the angular momentum, instead of being in the spin of the object, was actually in a moon orbiting around it. So people went looking for it. Where did they look? They looked in the Hubble archive, okay? Hubble had already taken images of 2000 OR10, and they saw this. In 2009 and 2010, Hubble took these images. So the bright spot in the center is 2007 OR10, and because it's a solar system object, it moves relative to the background stars. So there's lots of things like, you know, this thing and this thing. These are all background stars moving past. The things that are different in each image are the stars in the background. Is there something the same in each image? You betcha, otherwise I wouldn't be talking about it. There. They discovered that, yes, it did have a moon. So here's where it was in 2009. Here's where it is in 2010. Unfortunately, these 2 observations weren't enough to determine an orbit for it, so they don't know the actual mass of it. But we turned to the Herschel Space Telescope, and they were able to use far infrared observations to get a thermal emission profile for it and estimate its size. So, adding that back into the chart, you can see that the provisional designation for it here, we now have 7 of the top 8 Kuiper Belt objects with moons. Now, the really cool science behind it is, well, fine, you've got these icy things that have these icy moons, but you really couldn't have formed them as you formed the Kuiper Belt object. You think of Jupiter and its Galilean moons, and Jupiter forms here, and the moons form in a disk around them. How did these moons form? Not by accretion around the collapsing body, but rather via collision and capture. So the idea is that for all of these objects, something smashed into something else and collected a moon around it. Okay? So Hydra, Nix, Kerberos, and Styx, by the way, these are the actual sizes. Those are kind of tiny moons. All right? And Charon all have the same orbit. And we believe there was a very large smash produce the Pluto-Charon system, okay? And the same for all of these, that a collision produces captured moons. So it's actually adding to our scientific understanding of the formation of moons, which is kind of important, and it really hits home because amongst the planets, this one is believed to have had that same process happen. Our moon, using rock instead of ice, is believed to have formed when approximately a Mars-sized body hit the Earth about 4.5 billion years ago. So an appreciation of the frequency at which these collisions can happen and produce captured moons is greatly increasing with our knowledge of the Kuiper Belt. All right? Thank you. And that's our news from the universe for tonight. All right. Now we're going to go on to our featured speaker. And our speaker is Amber Straughn from NASA Goddard Space Flight Center. She likes to describe herself as an Arkansas farm girl turned astrophysicist. She did her undergraduate work at the University of Arkansas. Then she did her graduate work at Arizona State University. And she's down at Goddard Space Flight Center working on the James Webb Space Telescope. And she has a bunch of cool things about her. One of the things that's been highlighted a lot is that she is a pilot. She flies her own planes. And she tells me that that's fun, but the really fun thing is she got to go on the Vomit Comet. The hyperbolic, parabolic trajectory plane where you actually are weightless for how long?
About 20 to 30 seconds, and we did about 20 or 30 per hour.
All right, so so you're weightless for 20 to 30 seconds, and they do it 20 times in a row. All right, and she kept her lunch down. So, ladies and gentlemen, we have a hearty speaker tonight, Amber Straughn.
All right, can y'all hear me in the back? Y'all, I say you heard I was from Arkansas, so I say y'all. So great to see so many of you tonight. I'm really excited to be here to talk a little bit about an awesome new mission that we have coming up and to talk about some of the science that motivates this mission. So you've heard I'm from Arkansas, and really what got me interested in astronomy to begin with was the fact that I grew up in a rural part of the country. So I grew up in a tiny little town called Bee Branch, Arkansas, which I'm almost guaranteeing nobody in this audience has heard of. Middle of nowhere, north central Arkansas. Not a lot to do, but the sky was beautiful. So I grew up under this rural, dark sky, and that's really what got me interested in the stars from the time I was a little kid. And since that time, when I was a kid, I decided to I was asking all these questions about the universe and decided from a very young age that I wanted to pursue that dream, to find out what was out there, what was beyond what you can see with your eyes. And from the time I was a kid, one of the things that's really has captivated me about astronomy in general is that astronomy gets to the heart of our big questions. And these aren't just questions that scientists ask. These are questions that human beings ask. These are questions that we've asked over millennia that get to the heart of what it means to be a human being, of how do we get here, and what's the universe like? And then that big question that we're still trying to answer, which is, are we alone? And so many of our fundamental questions about the universe have been answered over the past many decades by telescopes. So we're able to learn a lot about the universe just from looking at the sky. Our ancestors, of course, learned about time. We measured time by the way stars pass in the sky. We learned, many centuries ago that there were certain objects in the night sky that moved a little bit differently than most of the stars did, and those, of course, turned out to be planets. And so for centuries, for millennia even, people have been looking at the sky and figuring out how the world works just from looking at the sky with your eyes. But of course, there comes a limit to what you can learn from looking at the sky with your eyeballs. And so we build telescopes to help us build on that knowledge. And as an astronomer, I've been really fortunate to observe at some of the world's biggest telescopes on the ground, telescopes in Hawaii and Chile. But there does also come a limit to what we can learn from telescopes on the ground, just from the simple fact that telescopes on the Earth have to look through the atmosphere. And so what do? Of course, we put telescopes into space. And the Hubble Space Telescope has been I believe, one of the most critical scientific instruments that human beings have ever built. So Hubble has completely transformed our understanding of the universe in fundamental ways, starting with the nearby universe of our solar system and then reaching out to the most distant things that we can see in the faraway universe. And so I'm here tonight to talk to you a little bit about some of the unknown things in the universe, dark energy and alien worlds, some of these big questions that we have. But I wanted to start off by talking a little bit, to preface this unknown stuff, with a little bit of what we do know and how we've learned that. And the Hubble Space Telescope has been instrumental in helping us learn about what our universe is like. And so starting in our own cosmic backyard of the solar system, Hubble has taught us many, many things about our own solar system, including this beautiful composite image showing aurora on Saturn. NASA, of course, also launches satellites that go out and visit these distant worlds in our solar system. So this is an image from NASA's Cassini telescope, which in just a few months will have its grand finale as it actually crashes into the planet. So be sure and check that out. One of the great things that Cassini has given us, I believe, in addition to all this incredible science, is just a perspective of us humans. And this is something that, again, goes back to those big questions that astronomy gets to about telling us about our place in the universe. And so this is an image from Cassini from beyond the orbit of Saturn looking back. And that little tiny dot is us. That's everyone you've ever known in that little tiny blue dot. And of course, this was the blue dot that Carl Sagan talked about and so much back in the early days and popularized astronomy in such a unique way. I have such a fond spot in my heart for Carl Sagan and all the great outreach that he did. But missions like Cassini have given us this grand view of what we are and help to probe those big questions of our place in the universe. And then very recently, NASA's Juno spacecraft has been sending back these absolutely incredible images of our planet Jupiter that sort of go beyond science and even get into art. This could be a piece of art in a museum. And then, of course, just a couple of years ago, we all remember the excitement of NASA's New Horizon mission, reaching Pluto and revealing this heart on Pluto, and revealing the structure of this outer planet, dwarf planet, that we'd never seen before. And so all of these missions have helped us learn more about our solar system. And then returning to Hubble, of course, branching out from the solar system, more distant. From Hubble, we've been able to observe star-forming regions within our own galaxy. So this is the Carina Nebula. And this image gives us an overall view of star formation. So lots of new stars are forming in this part of the universe, and stars are also dying in this part of the universe. There's this giant star here that's probably about to go supernova literally any day, or it might be 1,000 years, but it's a tiny span of time in astronomical sense. And then stars, of course, after they're born, they have winds that shed out the dust and the gas, and stars shine forth in these beautiful giant clusters. This is the image that came from the 25th anniversary of the Hubble Space Telescope just a couple of years ago. And then we all know that stars, when they live out their lives, they often go through these violent deaths, these explosions that can be either very dramatic, like the Crab Nebula that you saw in the introduction, or can be more gentle, stars blow out their atmospheres, like this example of the Butterfly Nebula. And so we know that our sun will someday undergo a similar process like this, where it will shed its outer layers, it'll grow into a red giant, it'll eventually engulf the Earth. Now this will be several billion years from now, so we don't have to worry about that. But I love the fact that these beautiful images from Hubble really tell us something about our origins. So these stellar explosions, like supernova, are the very events that seeded the universe with the elements that would eventually become planets and eventually become life. So the iron in your blood and the calcium in your bones was literally forged inside of a star that exploded in a supernova. And so what these images really show us is our sort of cosmic connection to the universe. And that's one of the things I love. This is an image of also, still within our own galaxy, of a star that underwent this really complex, confusing event. We still don't really know what's going on with this star, but it's shedding its layers or it's blowing a wind out into the surroundings. So many mysteries out there still. And then beyond our own Milky Way galaxy, we now, of course, know that there are many other galaxies. So this is a nearby galaxy that if you could get outside of our Milky Way and could look back on it, our Milky Way would look probably a lot like this. We think our Milky Way is with other galaxies, so they merge with other galaxies. In my own research, I study galaxy evolution broadly. I'm interested in how galaxies change over time, how their stars and their black holes form. And we think this process of galaxy collisions is a really key part of how all of that takes place, of how black holes grow. And we think that there's also gas in the universe that feeds into galaxies that help black holes grow over time. A lot about this process that we don't understand, but we think that galaxy mergers play a key part in the overall evolution of galaxies over time. And then of all the beautiful images that Hubble's given us over the past 27 years now that Hubble's been in space, if I had to pick my absolute favorite one, this would be it. So this is the Hubble Ultra Deep Field. This happened to come out when I was in graduate school, so this is one of the reasons I'm so fond of it. I did a lot of my dissertation research on this image. But this particular version of this image was about 11 days total that Hubble stared into space. And in this image, Hubble's looking at a tiny, tiny little piece of sky. So it's like looking at the universe through a straw. If you held out your pinky finger, you could cover up this teeny tiny little patch of sky. And every point of light you see in this image is an individual galaxy itself filled with hundreds of billions of other stars. And so really what Hubble has given us, in a fundamental sense, is the size of the universe. These deep images with Hubble were revolutionary, and they told us that the universe is filled with hundreds of billions of other galaxies, and all those galaxies with hundreds of billions of stars. Now, in addition to just being a beautiful image, we're able to take spectra of these galaxies, to take the chemical fingerprints of the galaxies, and learn about their distances. And so when we learn about the distances, we can actually make these images sort of 3D. We assign distances to them, and so we can sort of fly through the images in a sense, to get a bit of a sense of scale and a sense of distance for these images. So in the Hubble Ultra Deep Field, again, you notice a lot of interesting things. So you notice as we go deeper into the universe, the galaxies change. They start to look different. Nearby galaxies look sort of similar to our Milky Way, a lot of them. They have spiral arms. They're very large. They have organized structure. But as you get into the deeper universe, the more distant universe, you see a different picture. Galaxies are less well-formed. They're smaller. They're clumpy. They're different. And so learning about how galaxies change over the course of the last 13.8 billion years of cosmic history is still a really important part of astronomy. There's a lot about that process that we're still really need to push further. So as much as we've learned about the universe since we've put Hubble into space, since we started building telescopes on the ground, there's still really a lot that we don't know. And of all of these galaxies, of hundreds of billions of galaxies that we found, filled with hundreds of billions of stars, all of those galaxies, all of those stars, what we know now are probably trillions of planets. Every person, everything that you've ever known, still, all of that, only makes up about 5% of everything in the universe. And the rest of that is what I want to spend the rest of my time tonight talking to you about. So going back to that previous pie chart, so the 5% that we know about, the galaxies, the stars, the planets, That's what we know about. So look now at the 27% that is dark matter. So dark matter, what is it? We have no idea. But this poses a really, really interesting question to us as astronomers. So we don't know what it is, so how do we know that it actually exists? So we have a few clues. The first thing is by looking at spiral galaxies. So you take a spiral galaxy like this, and it looks like it's spinning, right? That's because it is. So back decades ago, astronomers looked at the motions of stars in spiral galaxies. Vera Rubin was actually one of the pioneers of this, an astronomer who did this work back in the 1960s, 1970s. And what you expect to see in spiral galaxies is that as you get out further from the center, you would expect the speeds of these stars and the matter to be slowing down. That's what Kepler's second law tells us that should happen. But that's not what we see. So all of these motions depend on mass, depend on the mass that exists from the center out to the stars. And so when we studied the motions in the outer parts of these galaxies, even out further than what we could see, what we found is that there should be more mass there than what we're seeing. There's something there that's causing the stars to move faster in the outskirts. Can't see it at all. And we know it's not gas because we can detect gas in other ways. So not gas, not stars, something hidden in these galaxies that are causing them to move in ways that are unexpected. The second big clue came in galaxy clusters. So galaxy clusters are also a really good way to measure mass. So we can look at individual galaxies and clusters and measure their speeds fairly easily, in fact. And when we look at galaxies and clusters, we find that they're moving way faster than they should be. So if it was only the galaxies, only the stars, then these clusters should have blown themselves apart, millions of years ago. But galaxy clusters stay together. So there's something there that we're not seeing. And in addition, in these galaxy clusters, we've also, Frank has already pointed out a little bit about gravitational lensing. So what's going on there? So we have this big mass of galaxies and gas, and then beyond that, we have background galaxies, and then over here we have our telescopes. So what's going on with gravitational lensing is that we're essentially seeing the background galaxies being lensed by the mass that's in between them. So this is what theory tells us we should see if there's a lot of matter out there, or dark matter that's hidden that we can't see. And of course, this is what we see when we take these Hubble images. So in these Hubble images of galaxy clusters, you see all these little blue arcs. In addition to the bright yellow galaxies, you see these background galaxies that have been stretched and lensed. So this is a smoking gun for dark matter that exists in these galaxy clusters. This is a very famous galaxy cluster image called the bullet cluster. This is actually two galaxy clusters that are crashing together. And so what you see here, again, all this sort of yellow, orange structures here are individual galaxies. The red, the pink and the blue here represents gas in the galaxies that we're able to image in X-rays. And so these two galaxy clusters are crashing together. And we're able to, again, look at sources behind the clusters. And what these images tell us is that all the dark matter is centered on the galaxies and not on the gas. So another third sort of independent clue that dark matter exists in these clusters. So we have all these different independent lines of evidence that dark matter is out there. And so we have a third way that we're able to learn about dark matter by looking basically how galaxies are distributed across the universe. And so just similarly, we're able to map out galaxies at different distances and measure their properties. And those properties tell us, again, that there's mass out there, that these galaxies are moving in ways that indicate that there's matter out there that exists that we can't see. So we don't know what it is. we have a better idea of what it's not. So we know that it's probably not regular stars or gas or planets, because we would be able to see those things. We'd be able to see stars that are bright enough. Dim stars, okay, we might not see the dim stars. Gas we can see from the way the stars are lighting up the gas. But really ordinary matter, baryons, neutrons, protons, and electrons, we would be able to see them in some way, and we can't. So we really don't think it's any of these things. Now, it might be some very, very dim stars, but if those stars exist, they would only be a tiny, tiny fraction of what we think has to be to make up this dark matter population. So we don't think it's regular stuff. We don't really think it's antimatter. So we know antimatter would annihilate with regular matter and produce gamma ray signals that we would be able to detect. We have gamma ray telescopes that would be able to see that. So we don't think it's antimatter. We don't really think it's giant black holes, sort of for the same reasons, because we would be able to see those observationally, see signatures of the black holes in other ways. We don't really see them. So what is it? Well, again, we don't know, but we think what it likely is some sort of yet undiscovered elementary particle that really doesn't interact with radiation in the same way that normal matter is. So that's what we think it is, but again, we don't know. All right, that's dark matter. Not very satisfying, right? We don't know what it is. Okay, dark energy. So almost 70% of the whole universe is made up of dark energy. So what is it? Any guesses? Yeah, we really have no idea what dark energy is. But similarly to dark matter, we know that it exists. And the really strange thing about dark energy is that it's completely confounding our ideas about how gravity works. So it's baseball season. Any baseball fans out there? Orioles fans? Yeah, I would hope so. Okay, so you have a baseball. You throw it up in the air. What do you expect to happen? It comes back down, right? That's our everyday experience of gravity. That's how gravity works. What dark energy tells us is that on large, large distance scales, that instead of pulling, the gravity pushes. So we experience gravity as an attractive force. And what all the physics, all the theory, all the observations are telling us is that at large distances, gravity pushes the universe. And this is completely confounding to everything that we know. Okay, so why do we think this? The first big clue actually won the Nobel Prize back almost 20 years ago now. So this was looking at distant exploding stars, supernovae in distant galaxies. And actually an astronomer right here at the Space Telescope Science Institute, Dr. Adam Rees, was one of the Nobel Prize winners for this really groundbreaking discovery. And so what is it about supernova? So supernova are what we call in astronomy as standard candles. So they have a certain brightness. You can sort of think of it as a light bulb. And so the further the light bulb is away, the luminosity or the brightness of the light bulb goes down. And that's just a very simple physics equation. You know, if you have a standard light, if you measure how bright it is, you can determine how far away it is. And so that's what astronomers were able to do with the supernova. And so we've known for years, since the days of Edwin Hubble back in the 1920s, that the universe is expanding. And so we know the universe is expanding. We know galaxies are moving away from each other. But if all that exists in the universe is gravity, then we would expect that the expansion would maybe be slowing down, maybe be constant. Didn't really know. But when observing these supernova, what we found was something really interesting, was that the most distant supernova that we could see were much fainter, or not much fainter, a little bit fainter than what we expected. And so what this told us was that the more distant galaxies that we were looking at with these supernova were moving away from us much faster than we expected. So that means the universe is accelerating in its expansion. Completely unexpected, complete surprise, but the universe is accelerating, something we found out almost 2 decades ago now. And so, again, by studying these supernovae was one of the ways that, that we found this out. And supernovae have this really great property that they're very constant. So they're normal stars that blow up, and they get really, really bright in a very short period of time, and then their brightness drops off. And so because of the regularity of the supernova, we're able to study them in detail and, again, determine the distances to galaxies, which is what confirmed this idea that the galaxies, the further galaxies, the most distant galaxies that we could observe these in, were moving away faster than we expected. So that's the first line of evidence. Second line of evidence is from the cosmic microwave background, which I'm actually going to skip because I'm running a little short on time. We can come back and talk about it if we want. But this third way was, again, by making these huge maps of the nearby universe and looking at how galaxies are distributed in space. And basically from doing this, we're also able to measure the speeds of distant galaxies. And this was sort of an independent confirmation of how distant galaxies were moving away faster than we thought they should have been. So it's sort of an independent way to measure this dark energy. And there are other lines of evidence that sort of all point to this idea that there's this mysterious force in the universe that's causing it to accelerate in its expansion. Okay, so we have no idea what's causing this. We see that it's happening. We don't know why. We don't know what it is. But we have a few ideas. So what could it be? So it could be some sort of intrinsic property of space-time, something about space itself that's causing the universe to expand. And so Einstein actually predicted this long, long ago. He ended up calling it his biggest blunder because at the time, basically, the leading theory was the universe wasn't accelerating, and now we find out that it is. So it's just some property of space that basically says that empty space is not really empty. It's always sort of creating new space. So that's the cosmological constant, really strange. So the second idea of what it could be is causing this acceleration of the universe is basically a new version of gravity, that we've got our theories of gravity wrong and that we need to modify them. So that would say that general relativity is not quite right on these scales, so maybe Einstein was wrong. And then the third idea, another idea, is that there's really just some kind of new energy field that we haven't really theorized yet. We haven't really figured out yet. So there's these three ideas, and we really don't know. People are sort of leaning towards the first idea, that there's this cosmological constant, but what we really need is more data. And of course, that's where the WFIRST telescope comes in. So the WFIRST stands for Wide Field Infrared Survey Telescope, and it is specifically designed to tackle this question. It's specifically designed to study this effect of dark energy and also of dark matter. So how is it going to do that? Well, one of the ways it's going to do it is to precisely measure galaxy shapes to infer the amount of dark matter that exists in the universe. And this goes back to this idea of gravitational lensing. So any galaxy that's in front of another galaxy is going to distort the shape of the background galaxies, and by precisely measuring those shapes, we'll be able to figure out more about how the intervening dark matter affects those galaxy shapes. And then another way is by very accurately measuring the positions between galaxies. So it turns out that these positions between the galaxies, so if you think of the universe in a three-dimensional sense, the positions that we measure between the galaxies traces directly back to shortly after the Big Bang and to what happened in the universe early on. So that gets back to the very early imprints in the universe for dark energy and dark matter, and all the contents of the universe will help us learn more about that. And then getting back to this idea of supernova, This telescope will allow us to take new surveys of wider swaths of the sky that will help us to determine more supernovae, basically to narrow down those measurements and to pinpoint some of these physical quantities of the universe that will help us to establish better distances to these galaxies, just to hone in on these parameters that describe the overall physics of the universe. And so we have these three fundamental things that WFIRST will measure about the universe: the galaxy shapes, the positions, and the distances to these distant galaxies. And so these things will give us hints into different parts of the universe about how structure grows over time. Not only the galaxies, but how the galaxies weave together in this overall cosmic web. And then also about how the expansion history works. Again, we know the universe is expanding. We know that it's accelerating, but we don't know what the history of that has been. Has it always been accelerating at the same rate that it is now? So the further out we can push these measurements and the more precise we can make them, the more we can learn about these physical mechanisms that are taking place. And so what this will eventually allow us to do as we hone in on these measurements is really to allow us to determine how the universe will continue, how it will end. If it will end in a big freeze, in a big rip, all of these different scenarios that will allow us to see how we think the universe will continue on. So this telescope is specifically designed to get at these questions of dark energy and dark matter. But the really cool thing about the technology that's going behind building this telescope is it's going to allow us to look back also at the 5% and about one of the really interesting parts of the 5%, which is exoplanets. Now, when I was a kid, we only knew of the planets in our solar system. Now, thanks to NASA's Kepler telescope, we know that planets are literally everywhere. The Milky Way is teeming with planets. Statistically, every star in the night sky has at least one planet around it. That's a paradigm shift. You know, even 15 years ago, we didn't know this. And so what WFIRST is going to allow us to do is a couple of different things for exoplanets. So it's going to help us, first of all, find more nearby exoplanets in a different part of the sort of solar system space or the exoplanet system space. And then it will help us directly characterize some of the closest exoplanets that we know about today. So of all of these different planets, this is of course an artist's illustration. Unfortunately, we don't know the details of these planets. Wouldn't it be great if we could actually draw all the planets we know about in a poster like this? But we don't know what they look like. We know there are thousands of confirmed exoplanets, and again, statistics just tells us that there are hundreds of billions of exoplanets in our galaxy, and there's no reason to think they wouldn't be in other galaxies as well. We don't know what they look like, but WFIRST will have the capability to directly image some of the closest and brightest ones. So how do we do that? So all of our best images, actual images of exoplanets to date, are these tiny little blobs. Not very pretty, right? So WFIRST will have an instrument called a coronagraph, which is basically an instrument that blocks out the very, very bright light of a star and allows us to focus in on the planets to better image the planets that are orbiting that star. Now, this is very difficult. Stars are very, very bright. Stars are tiny, stars are bright, planets are tiny, and they're hard to see. And so doing this is extremely difficult, but WFIRST is going to have a new capability to do this in a new way. Now, it's not going to be this detailed. It's not even going to be close, so this is a little misleading. But it's really going to be a new technology, a new way to do this in a really new way. And so just to give you a sense here, this is showing you sort of the area that Kepler looks for and all those exoplanets that Kepler has found. We're launching a telescope called TESS next year in early 2018. It's the Transiting Exoplanet Survey Satellite from NASA. So that particular telescope is going to look particularly at the closest exoplanets in our Milky Way and look close in at the planets that are really close to their star. So what WFIRST is going to do is expand that. It's going to look for the bigger planets that are orbiting further out from the stars. And so it's basically going to help us to, with these 3 telescopes and others, help us to sort of complete the census of exoplanet systems in our nearby Milky Way galaxy. So one of the really neat ways it's going to do this is by a technique called microlensing. So this goes back to the same physics principles as gravitational lensing, is when you have one object that passes in front of another. And in this particular case, you have a star and a planet that's going to pass in front of a background source. And what happens when you have this particular arrangement is that we get a very unique spectral signature that we can easily detect, and that tells us that we have a planet. Now, where's a good place to look for this? In the disk of the Milky Way. If we look right down the throat of the Milky Way galaxy, where stars are packed in, then you're very likely to have this occurrence happening pretty often. And so what we expect with the WFIRST microlensing survey is to see this microlensing effect, these planets and stars passing in front of background stars, to happen very often. And so this is a plot that shows down here on the x-axis, this is distance of the planet from the star. AU is astronomical units. 1 is the Earth's distance from the sun. And here's the planet's mass. So the Earth right there, 1 and 1. So what Kepler has found, again, has been mostly sort of smallish planets really close to their stars. What WFIRST is going to do is push out to find planets that are more like our gas giants that are orbiting stars, close to our, to our solar system. And so WFIRST has all of these really sort of grand goals. It's really being built to answer some of the most fundamental, puzzling questions that we have in astrophysics today. So how in the world are we going to do this? The key thing about WFIRST is the enormous size of the camera and of the pictures that it will take. So that little square here is the size of the Hubble's camera, so 1 pointing with Hubble. So that Hubble Ultra Deep Field I showed you, all the images of the planets, of the nebulae. So WFIRST will have an area that's 100 times the area of Hubble, and this is critical also with the same depth and clarity that Hubble has. Now we have telescopes on the ground that are able to take these big wide images, but they are very shallow, they're very low resolution, okay? And so what you really get with WFIRST is sort of the best of both worlds. You get the depth and the clarity and the precision of Hubble with this gigantic field of view, this giant area. And so this is basically going to be Hubble times 100. So with this telescope, again, we hope to sort of start to unlock some of these mysteries of dark energy. We hope to learn more about some of the nearest exoplanets in our Milky Way. But this telescope is also going to be an incredible tool just for general astrophysics. So all of these surveys that WFIRST will take that will help us learn about dark energy, help us learn about exoplanets, will be available to astronomers and to the public to do what I think will be really incredible general astrophysics. So just to give you a couple of examples of that, as I mentioned, to find exoplanets, the best way to do this is to look down the throat of our own Milky Way galaxy. So again, here we have the Hubble field of view. JWST is very similar to Hubble, and then it sees a little tiny picture on the sky. But again, WFIRST, we get 100 times the area. And so when we survey the center of the Milky Way galaxy with WFIRST, in as few as just, a few, less than 10 pointings of WFIRST, you basically survey the entire center part of the Milky Way galaxy, and you're able to learn so much more about all of these different ranges of astrophysics. So what's going on with the supergiant black hole at the center of our galaxy? What's going on with how young star clusters form? So a huge range of astrophysics that we'll be able to do with these surveys. And then I mentioned that the Hubble Ultra Deep Field was my personal favorite, because that's what I did a lot of my dissertation research on. So with the Hubble Ultra Deep Field, that one little tiny piece of sky revealed 10,000 galaxies, but one pointing with WFIRST at 100 times the field of view. That's easy math, right? We're going to see 1 million galaxies in just one image with WFIRST. Again, with the same depth and clarity that we've been able to achieve with Hubble. And so I really believe, me being an extragalactic astrophysicist, that this telescope is going to revolutionize the way that we understand how the universe works over the course of cosmic history. It'll change the way that we understand the evolution of galaxies over time. So all of these different things that we have planned for the telescope, again, these specific surveys to figure out how dark energy works, how exoplanets work. I think for me, one of the things, we're having a science conference right now here at the Institute on WFIRST science. So a bunch of astronomers are here from all over the country, all over the world, to think about what this awesome observatory is going to do. And one of the comments I heard yesterday, I think, is probably the most significant thing I've heard, and it was in reference to the Hubble Space Telescope. And the comment was basically that, Hubble was built to answer a few key science questions of its day. But if you build a telescope, if you build a really extraordinary machine, then the community is going to find new and novel ways to use that machine to find things about the universe that we never dreamed of. And to me as a scientist, that's the most exciting thing about being a scientist, is we build these missions with these very specific questions in mind, these specific things that we want to answer. But the fact is when we build these telescopes, we find answers to questions that we didn't even think to ask when we were building them. And that overall is, I believe, the promise of the universe and why we build these missions. Thanks so much. Thank you. So I think we have time for a few questions.
Oh, yes, we have plenty of time.
Alrighty. So I see lots of hands.
Okay. Why bother with the James Webb if you had the W?
That's a great question, because I believe.
Did you ask that question?
So I didn't mention. I should have mentioned. We're building it now. This telescope. We already have the mirrors for the telescope. The mirrors, this is sort of an interesting story. So the mirrors were donated to NASA by the Department of Defense. They were meant to see wide fields very deeply. But the DoD gave us these mirrors, right? So we're not going to look down, we're going to look up with these mirrors. We're planning to launch in the mid-2020s for WFIRST. But, oh yeah, you're right. We're also building this other thing at NASA right now. So the James Webb Space Telescope is going to be launched next year. And the Webb Telescope is, it's designed to answer different questions. The Webb Telescope in many ways is really the scientific successor to Hubble. So Webb is going to see further into the infrared, so it sees a different part of the spectrum. So WFIRST is also an infrared telescope, but it only sees a little bit into the infrared. And again, the key thing about WFIRST is its huge, wide field of view. So Webb is going to be similar to Hubble in that it sees a little part of the sky, but Webb is going to see much, much deeper. So Webb will see deeper than Hubble, and Webb will see deeper than WFIRST.
So it'll be more resolution with the Webb.
That's right. Yeah, so more resolution, but also because it sees further into the infrared part of the spectrum, it's able to see different things. So, for example, I showed the sort of fly-through of the Hubble D field. And so in the D field, we come to an edge of what we can see with Hubble. And that's really because Hubble cuts off at the near-infrared wavelengths. So to see the most distant galaxies, to see, for example, the first epoch of galaxies that were born in the Big Bang, we need to see further into the infrared part of the spectrum. And that's exactly what Webb is designed to do. Webb will also have instruments on board that are designed to do transit spectroscopy. So Webb has some really, really incredible high-resolution spectrographs that WFIRST doesn't have. WFIRST has low-resolution spectrographs, which will allow us to do a different set of science. So Webb and WFIRST are different, but they're complementary. And so what the astronomer's dream is, of course, to have both of these in space at the same time. Because one of the cool things that WFIRST will be able to do with this huge wide field of view is find some of the most rare objects. Okay, so you can imagine the biggest, hugest distant galaxies, so galaxies that are very distant, but for whatever reason happen to be huge. But so they're probably really, really rare. And you can come up with ideas of other things like this that are very rare. And so you need a wide field of view to see these rare things. And so Webb would be able to find these rare things. WFIRST would be able to find the rare things, but we might want to go back and take detailed spectra of them. That's what Webb would do. And so our hope is definitely that WFIRST will launch in the mid-2020s, so we'll have some overlap of the two telescopes. And if we're really lucky, fingers crossed, Hubble will still be operating then. Of course, we don't know. Hubble's doing really great right now. Wow, to have all three in space at one time, that would be awesome. Mm-hmm.
What is WFIRST different from the Hubble that you can have the same resolution but a larger field of view?
Yeah, so a couple of things. First of all, it's just the detector technology. Hubble has a sort of limited amount of space and places where you can actually place the detectors. And of course, we've been to Hubble now for the last time, so we've done the last upgrade on Hubble. But for WFIRST, we're specifically focusing on these detector arrays that are just huge, they're massive. So it's really just having those detectors, those advanced detectors, and also detectors that are just big. It's just a big focal plane. And then also having just the configuration of the telescope itself makes it such that sort of the focal length of the telescope allows it to have this wide field of view. So if you've done...
how does the size compare to that?
Oh, that's a good question. Let me get back to that. So really just, the configuration of a telescope, the focal length and all of that, gives it sort of its parameters of how it can see the universe. So Hubble is sort of this sort of long tube, like what you think of as a backyard telescope. WFIRST is, people sort of affectionately call it a stubby Hubble. So it's the same mirror size as Hubble, but it's sort of shorter. So it's got a different focal length, and so it just allows it to see the universe in a different way. So it's just sort of built differently, and then it has this different detector array. So a combination of those.
Let me make sure that we mention the wavelength coverage, because Hubble can also go into the ultraviolet, which is extremely important for astronomy. You cannot do ultraviolet astronomy from the ground, and right now Hubble's the only game in town for that.
That's right, yeah, so wavelength is really critical here. So as astronomers, we want to see the universe in as many wavelengths as we can, which is why we build all these different telescopes to see the universe in different ways. And yeah, as Frank said, Hubble's the only telescope we have right now that can see the ultraviolet universe. And Galax data, we have some. So we have a little bit of other capability, but right now Hubble is the prime telescope for ultraviolet, visible, and then Hubble can see a little bit into the near infrared. So WFIRST is planned to see in the infrared, and then Webb will be infrared plus out to the mid-infrared. So it's just sort of about covering the whole spectrum. And then I saw a hand back here, but to answer your question about size, so Hubble is about the size of a school bus, roughly. Its mirror is 2.4 meters. That's the same size as the WFIRST mirror. Webb its primary mirror is 6.5 meters, so about 22 feet across. So Webb is huge. To go back to this other picture here, Webb is by far the biggest telescope that we've ever sent to space. Let me get back to it. Where'd it go? There we go. So top to bottom, this is 6.5 meters, about 21 feet. What you don't see in this image is it's got a giant sun shield that's about the size of a tennis court. Yeah, so this model shows this structure here is about the size of a tennis court. So top to bottom, it stands a little over 3 stories tall. So it's by far the biggest telescope we've ever sent to space. So Webb is definitely unique in that sense and how big it is. That of course means we have to fold it up to launch it and send it into space, and it's very complex. And we have the best engineers in the world working on it, so we're confident it's going to work. All right, I saw a question back here. Yeah.
I just have a quick question. So you had an image that showed the visible matter and the dark energy and the dark matter, but you had it narrowed down to percent. So how were you able to figure out 68 and 27 and 5?
That's a great question. So a lot of that is set on constraints that we measure from the very early universe. So that very colorful image I showed with the cosmic microwave background. So the cosmic microwave background is sort of this imprint, this image of the baby universe. That it's about 400,000 years after the Big Bang. And we can basically measure sort of details about that image that tell us a little bit about what the evolution of the universe will be and what the different percentages will be. So this gets deep into theoretical cosmology. So most of what I've talked about tonight is observational cosmology or observational astrophysics. I'm an observational astrophysicist. I use data to study the universe, but of course there's this whole other set of astronomers that we work really closely with that do complete, just theory, just physics about how the universe works. And then there's sort of on that same scale, there are astronomers that work mainly with computer systems that develop computer models of how the universe works. And so all of these sort of different types of astronomers work together. And so the theoretical astrophysicists are the ones that work out what these different percentages should be. Now, we don't think those percentages have always been that. So, for example, the universe, as I said, as we know, is expanding. And so the volume of the universe is getting bigger over time. So we think these percentages have changed over the course of time. So it's a complex, I don't know if that's a satisfying answer. It's a complex question with a complex answer.
All right,
but there's lots of different ways of observations that lead to us arriving at those numbers.
As one of those theorists, I can give you a real short answer. The expansion of the universe starts out decelerating and then takes over as accelerating. The timing of that changeover from when it goes from decelerating to acceleration is critically dependent on these percentages. So by doing our observations, finding the expansion rate of the universe over time and being able to get that down, that's one of the major ways that we're able to get the percentages better. Okay?
Thank you.
How about here?
Yeah. Yes, on that same point, so 27% dark matter, does that mean that the mean density of the universe is now greater than the critical density, meaning that it's of finite volume and closed? This is also for Dr. Summers, too, if you can. But beyond that, if the universe is also expanding, meaning the space fabric itself is moving in some unknowable way, how then do you calculate the volume? And is there a contradiction here?
Wow, that was a lot. I'm not sure I can answer all of that, but so yes, we know the universe is expanding. We know the volume is constantly getting bigger.
So it's closed in finite volume at this point?
We don't know.
We don't know. Our best observations tell us that the universe is flat. These are all still. So we're pretty sure that the geometry of the universe is flat. We know that it's expanding. We know that it's accelerating. We think the volume is getting bigger. But again, the best theories of dark energy tell us that empty space is constantly creating new space. Right? And so even though the volume is getting bigger, so the density overall should be going down. So in the past, the fraction of dark matter would have, for example, been greater. The fraction of baryons would have been greater. So dark energy had less of an effect early on in the universe. Okay, so the effect of dark energy is getting greater because the universe is accelerating. Do you have anything to add? I know, I totally cleared that out for you, I know.
You're thinking about energy density, and
Yeah.
matter energy density goes down over time, but if the cosmological constant is constant, then its energy density stays constant over time, which means once it starts to dominate the universe in its energy density, then the universe starts accelerating. And that's one of those.
Which is what's happening.
And
And of course,
yeah.
and of course, this isn't the first time that the universe has accelerated, right? We're pretty sure that early on in the universe there was a period of inflation. So that was a time of extreme acceleration. So it changes over time. But again, so many of these are open questions that we don't want to really answer to. Yeah, you.
Okay. So I had a question. Would WFIRST be able to answer whether supernovae are composed of single degenerate or double degenerates, or no?
So I do not know the answer to that question. I study galaxies. Are there any astronomers in the audience? I see some astronomers. No? I don't know. I really don't. I mean, the whole point of the dark energy surveys for WFIRST is to use these objects as standard candles. And so, we're pretty sure that they are standard candles. We will, of course, get tons of spectra of these supernovae, and so we'll be able to study the physics of the supernova also in greater detail with WFIRST. And the same thing with Webb. I wanted to see, I see a few kids in the audience, or younger folks. Are there any younger folks that have questions? I'm trying to give you a chance. It's all good. I just like to give you a chance.
Okay, other questions? Start down here.
Are there any plans to build a larger telescope than the Webb?
Yes! So astronomers are always dreaming of larger telescopes. So yes, we definitely hope for larger telescopes. Webb is, like I said, huge. It's the biggest telescope we've ever sent to space. You can get a little bit of sense of scale just from this image, from seeing, there's a person right here, right? There's a person, right? He's looking, so it's big. This is not the biggest telescope. Of course, we have bigger telescopes on the ground right now. It turns out it's a whole lot harder to build telescopes in space than it is to build them on the ground, right? If something breaks on the ground, it's pretty easy to go fix it. Something breaks in space. In the case of Hubble, we were able to send astronauts up to fix it, but I'm not going to be able to do that with Webb. Webb's going to be about 1 million miles away. I'm not going to send humans to fix it. So space is hard, but we do have hopes of putting bigger telescopes into space. So right now at NASA, there are studies going on, these teams of astronomers that have gotten together and are studying specific concepts for the next big telescope after WFIRST. So there are 4 of these teams, and they're each focused on different things. One is studying an X-ray focused telescope. One is studying a giant telescope that would focus in on exoplanets. One is studying an infrared interferometer telescope, and then one is studying basically sort of a super Hubble that would do sort of UV to infrared astrophysics in space that would be even bigger than Webb. So yes, we hope so. We hope so. Again, Webb is launching next year. So excited! We can say that now. It's just like a little over a year away. And then WFIRST launches. Again, in the mid-2020s is what we hope. So this next big telescope will be selected in the next several years. So these big telescopes like Hubble and Webb and WFIRST are generally selected every 10 years. So these are part of what's called decadal surveys, that some of you may have heard of. So every 10 years, astronomers from around the world get together and ask, what are our biggest questions? So they prioritize the biggest astronomy questions. And then they all fight over them and then finally agree on them. And these come out, these big questions come out in what are called decadal surveys, astronomy decadal surveys. And then with those big questions come the technology that we need to answer the questions. So in 2000, that technology was Webb. In 2010, it was WFIRST. So 2020 is coming up. So in 2020, or it'll actually probably be 2021, we'll find out what the next big telescope is. So we don't know. There are 4 candidates. We'll see which one comes up on top in the next few years.
But I will note that I did mention that Hubble was the last ultraviolet, telescope, so it's I personally think it's highly likely that whatever is the bandwagon goes behind in 2020 should have some ultraviolet capability. That would be my preference at least.
Ultraviolet is definitely unique, and it's one of those parts of the electromagnetic spectrum that we can really only get from space. A good chunk of infrared is like that too. You can't observe infrared from the ground, but large parts of it are completely blocked or partially blocked by the atmosphere, which turns out to be really good for humans, not so good for looking at stuff above the atmosphere. So having infrared telescopes in space also is really important.
All right, let's go for somebody in the back. Baseball cap in the back.
Dark energy, dark matter, is there any difference between those two and nothing?
Astronomers have this annoying habit of, if they don't know what something is, they call it dark. And again, we know that these elements of the universe are out there. We have all these different lines of evidence for both, for dark energy and dark matter, that tell us that it's there. It's having observable effects on the universe. So it is something. Dark matter is something that gravitationally interacts with other matter, and we observe that. Dark matter is affected by gravity. And again, we see that from the rotation curves of spiral galaxies. We see that from how galaxies and clusters move. We see that from the lensing. And similarly with dark energy, we see all these different clues that point to there's something out there that's causing the universe to behave like it is. So it is something, it's not nothing.
Just to follow up, the percentages you had has something. Is there a percentage of nothing?
So they're a percentage of the overall stuff of the universe. So, even empty space isn't nothing. That's basically what dark energy is sort of telling us. Classical physics tells us that empty space is empty. But quantum mechanics tells us that empty space is not really empty. That it's sort of always fluctuating. It always has this, that's one of the theories, of dark energy, one of the candidates, that it has this sort of vacuum energy, this part of space-time that is, because of just the way it is, it has this quality of having this energy. Maybe take one more, and then my throat's, I'm sorry, I'm getting over a cold. My throat's about to give way.
Yes, you.
Back to the telescope again. You said there was one group working on an X-ray telescope, but then way at the beginning there was an X-ray image of the Crab Nebula. So I'm wondering how we got that image, and then also if it's possible for there to be a gamma ray telescope, or if that's useful. Or
No, that's a great question.
Perfect question to ask a NASA person.
Yes, all of the electromagnetic spectrum, so yes, we have an awesome X-ray telescope in space now. That's called the Chandra X-ray telescope, and it's been up there a long time. So it's been doing great X-ray astrophysics for a very long time. The image I showed of the galaxy clusters with the sort of pink and blue. So the pink and blue was the signatures of the gas in those galaxy clusters. It's really hot gas, and so it emits in the X-rays. And so we do have this awesome Chandra X-ray telescope, which has been doing fabulous things. One of the candidates we're studying for the next decadal survey is also a new X-ray telescope in space. And then gamma rays, yes. We also have gamma ray telescopes in space. The Fermi's telescope it's been up now, almost 10 years, almost a decade, I believe. And it is primarily focused in the gamma rays. And so it's actually done a lot of cool recent study. You can go look up later, study the details, but of the Milky Way Center, and of looking for gamma rays from these basically antiparticle annihilations that would produce gamma rays, so a potential candidate for dark matter. So there have been some really interesting recent studies from Fermi on this gamma ray excess in the plane of the Milky Way. So yes, we at NASA build as many satellites as we can to observe the whole electromagnetic spectrum, which does serve to give us this broader view of the universe. It helps us put together the story and tell a complete picture of what's going on in the universe. Yeah.
All right, her voice is giving out, so we're going to have to end the questions here. I will remind you that Monday, July 10th, David Charbonneau, How to Find an Inhabited Exoplanet. Irini, come on down. Irini Lambrides, I guess is that how you pronounce your last name? Close enough, okay. She will take people across to the Maryland Space Grant Observatory if you would like to look through the telescope and see what's up there. And let us one more time give Amber a warm round of applause. Stuff. Mass.